Right, so in this lecture we're going to continue talking about theorems that we can use to determine whether an infinite series is convergent or divergent. So this one, 11.4, is about the comparison tests. And that may sound familiar, and it should, because we did a theorem about improper integrals that was also called comparison test, right? And this one works in almost exactly the same way. Okay? So it's like this. Theorem. This, of course, is called the comparison tests. Okay, let an be a sequence with positive terms. Okay. Now, two parts, just like for the comparison test for improper integrals. First part says, suppose that for all positive integers n, an is less than or equal to bn. So we'd say that an is bounded above by the sequence bn. So this part says this: if the sum from n equals 1 to infinity of bn is convergent, then the series sum from n equals 1 to infinity of an is also convergent. Okay? So it's saying if you can find another series whose terms are all larger than the terms of the series you're studying, and the series with the larger terms converges, then the series you're studying converges as well. Part 2 is probably what you're expecting. Suppose that for all positive integers n, Cn is less than or equal to an. So now we're saying an is bounded below by Cn. Now, if the sum from n equals 1 to infinity of Cn is divergent, then the sum from n equals 1 to infinity of an is also divergent. Okay? So if you can find a series whose terms are smaller than the one that you're studying, and it diverges, the one that you're studying diverges as well. Okay? And again, these only go one way, all right? Just like for the comparison tests for the improper integrals, you know, if I have a sequence that bounds an above, bn bounds an above, and it diverges, the series of bn diverges, that doesn't tell me anything. Okay? Similarly, if you can find a sequence that bounds an below, and that corresponding series converges, again, doesn't tell you anything. Okay? Oh, and there's all all the terms of Cn definitely need to be greater than or equal to 0. Yeah, so all the sequences here need to be positive. If you don't have a positive sequence, then this no longer applies. All right, so let's see how this works. So, example, determine whether the infinite series sum from, let's see here, n equals 1 to infinity of 1 divided by 2 to the n plus 1 is convergent or divergent. Okay. So, the way that I think about this is like this. First of all, we're not interested in finding the sum of this thing, which is good, because I don't know how you would do that. Now, if I'm interested in determining whether it's convergent or divergent, and I'm going to use the comparison test, then what I'm going to have to do is I'm going to have to come up with another series that is related to this by some kind of inequality, whose behavior I can actually figure out. Okay? And when I say behavior of a series, I'm always referring to whether it's convergent or divergent. Okay? So I look at this and I say, you know, the thing that's most annoying me about this sequence is the fact that there's a 1 here. If there wasn't a 1 here, this would just be 1 over 2 to the n, which you can actually write as a geometric series, right? Okay, so get rid of it. So 1 over 2 to the n, that's the same thing as 1 over 2 to the n. All right, now, of course, getting rid of it has some consequences. It will no longer be equal, right? What will be true, though, is that this will be larger than if you had that 1 there in the denominator. Okay? And that's because you just cut out a 1, so that made the denominator smaller. If you make the denominator smaller, then the whole fraction gets larger. Okay, so I have this new sequence, which all the terms of this sequence are larger than the terms of this sequence. Okay. Now, let's see what happens if we look at the sum from n equals 1 to infinity of 1/2 raised to the nth power. Well, according to our theorem on geometric series, this is convergent because 1/2, the common ratio, has an absolute value that's less than 1, right? So this is a convergent geometric series. Okay? And, you know, the theorem also tells us what it converges to, but that's not really important right now. All that we need to know is that it is convergent to something. All right. Now, according to part 1 of our comparison tests theorem, we found a sequence that has larger terms, and the series corresponding to that sequence converged. That means that the one that we're studying converges as well. Okay, so by the comparison test, the sum from n equals 1 to infinity of 1 over 2 to the n plus 1 is convergent. And that's it. Okay. So that's at least one example of how the comparison test can be used to determine that a series that you're dealing with is convergent. Of course, we're going to do another example. All right, this one, same directions. We're trying to determine whether it's convergent or divergent. But this one, I want to be 1 over the square root of n minus 1. Wait a second. That should actually be the sum from n equals 2 to infinity. Because, you know, if it's n equals 1 to infinity, then that's a problem because the square root of 1 is 1, and then 1 minus 1 is 0, so then you'll get 0 in the denominator. So yes, we're only talking about 2 to infinity now. That's not going to make a huge difference, it's something that I, as your instructor, should keep track of. Alright, so once again, you look at this and you're like, come on man, why do you have to have a minus 1 there? If you didn't have that minus 1 there, this would be easier to deal with, right? Okay, so get rid of it. Just have 1 over the square root of n. Now there are some ramifications to doing that, of course. You just made the denominator larger, so that means that this thing is smaller than the original terms of the sequence. Now, this thing right here, the square root of n is also known as n to the 1/2 power. So, what we're dealing with here is the sum from n equals 2 to infinity of 1 over n to the 1/2 power. That's a B-series. Okay. And 1/2, I'm pretty sure that's not greater than 1. So according to the P-series test, which we discussed in the last lecture, this is divergent. Okay, so this is a divergent P-series. Okay. All right, now let's look at what we're doing here. We found a sequence which has smaller terms than the terms of the series that we're studying. Okay? So we found a sequence that bounds the series that we're studying below. Okay? We found that this series with the smaller terms is divergent, so that means the series that we're studying is also divergent. Okay? So we just have to say, by the comparison test, the sum from n equals 2 to infinity of 1 over the square root of n minus 1 is divergent. Okay. Let's see. Let's do another one. Okay, this one is, let's take a look at this. This is sum from n equals 1 to infinity of 6 to the n divided by 5 to the n minus 1. Okay, and once again, we're trying to determine whether it's convergent or divergent. Okay. And so once again, we just say to ourselves, you know, if this 1 weren't here, it'd be easier to deal with. Okay, get rid of it then. So 6 to the n divided by 5 to the n. Now, again, that has consequences. If you remove that negative 1 from the denominator, then you're making the denominator larger, which means that the whole fraction is going to be smaller. So this is smaller than 6 to the n divided by 5 to the n minus 1. Now, 6 to the n divided by 5 to the n, that's the same thing as 6/5 raised to the n. So if we were to examine the series, sum from n equals 1 to infinity of 6/5 raised to the n, that's a geometric series, right? And specifically, since 6/5 has an absolute value which is greater than 1, or not less than 1, I should say, that means that this is a divergent geometric series. So this is a divergent geometric series. Okay. And since it's a divergent geometric series, and it has smaller terms than the series we're dealing with, then again, part 2 of our comparison test theorem says that the series we're studying is divergent. So again, by the comparison test, the sum from n equals 1 to infinity of 6 to the n divided by 5 to the n minus 1 is divergent. And that is that. Okay, let's do one more example of this type. Same directions, of course, and this time, this is going to be the sum from n equals 1 to infinity of 1 divided by the cube root of 3 times n to the 4th plus 1. Did I get that right? Yes. Okay. Alright, so once again, if that 1 weren't there, this would be easier. So get rid of it. Okay? If you get rid of the 1 in the denominator, then you'll be making the denominator smaller, which means that the whole fraction will be larger. Okay, so what we're dealing with here is 1 divided by the cube root of 3n to the 4th plus 1. Well, that's going to be smaller than 1 divided by the cube root of 3n to the 4th. Alright, now that, let's just notice that this is the same thing as 1 over the cube root of 3, whatever that is, times 1 over n raised to the 4/3 power. Okay? Now, if we take the sum from n equals 1 to infinity of 1 over the cube root of 3 times 1 over n to the 4/3 power, well, it's not quite a p-series. Strictly speaking, though, it's a constant times a p-series. because this is a sum, so that means we can use the distributive property to just factor this this constant out of the sum. So then this becomes 1 over the cube root of 3 times the sum from n equals 1 to infinity of 1 over n to the 4/3. And you can always do that with constants and sums. You can always factor out the constants. If the series is convergent, then it'll just converge to that constant times whatever the series converges to. And if it's divergent, then it doesn't even make a difference. Because, I mean, you multiply a series by a constant, that's not going to change whether it diverges or converges. So anyway, now this thing is a convergent p-series, because 4/3 is indeed greater than 1, right? So this is convergent since the sum from n equals 1 to infinity of 1 divided by n to the 4/3 power is a convergent p-series. All right, so then once again, you've got a series with terms that are larger than the terms of the original series, and the series of the larger terms converges. All right, then that means the series with the smaller terms has to converge as well by part 1 of the comparison theorem. So by the comparison test, the sum from n equals 1 to infinity of 1 divided by the cube roots of 3n to the 4th plus 1 is convergent. And that's that. Okay. All right, so now I just want to take a minute to talk about the following issue. So in all of the examples that I've displayed so far, there's been sort of an easy way to delete something and then simplify it, and then you could deal with that series, right? That isn't always the case. Okay? Here's an example where that's not true. So for this example, we're going to be talking about 1 over 2n plus 1. All right, so you say to yourself, well, I don't like that 1 in the denominator there, so I'm going to get rid of it. So I get 1 over 2n. But then that's actually larger than 1 over 2n plus 1, right? And okay, that's something, right? But now, if you look at the series n equals 1 to infinity of 1 over 2n, that's divergent. Okay? So now the sort of obvious simplification of this thing, it's divergent, but it's also larger, so that doesn't really tell us anything. Okay? Comparison test would only be applicable if this were like smaller and the series were divergent, or if this were larger and it were convergent. Neither of those are the case, so we're going to have to do something else here. Yes. In this case, we're going to use another theorem. This one has a similar name, but it's quite different. this one is called the limit comparison test. Okay. So, suppose that the sum from n equals 1 to infinity of an and the sum from n equals 1 to infinity of bn are, well, they're both infinite series with positive terms. So these both have positive terms. I should say all positive terms. That is to say, none of the terms are negative or zero. Have all positive terms down here. Here we go. Now, if the limit as n approaches infinity of an divided by bn is a positive real number, so that means greater than 0 but less than infinity, then either both series converge or they both diverge. Okay? So in other words, you have a series that you're studying, you come up with another one. If you know the behavior of that one, and you can take this limit, and it's positive and finite, then that means that they're going to have the same behavior. Okay? So let's look back at this example that had us a little bit frustrated before. This one right here, I'm going to look at the sum from n equals 1 to infinity of the obvious simplification, which is just 1 over 2n. Now, I claimed before that this is divergent. I'm going to show you why that is now. This is just 1/2 times the harmonic series. And so that's divergent because the harmonic series is divergent. It's the p series with p equals 1. So this is divergent since the sum from n equals 1 to infinity of 1 over n is a divergent p series. Okay? Okay. So that's at least one series whose behavior we know. And it at least looks a lot like that one, right? Perhaps the limit comparison test, therefore, can give us some insight into how that behaves. So, what we need to look at here is the limit as n approaches infinity of, let's see here, an, I guess, would be 1 over 2n plus 1, and bn, I suppose that would be 1 over 2n. By the way, you might be wondering, how do you know which one you should put on top? The answer is it doesn't matter. If one of these is positive and finite, then you can flip the whole thing, and then that limit will also be positive and finite, so it wouldn't matter at all. Okay, anyway, this is the same as the limit as n approaches infinity of 2n divided by 2n plus 1. And as n approaches infinity, this approaches 2 over 2, which is 1. Okay? And 1 is a positive real number, right? Positive and finite. So, by the limit comparison test, since this series diverges, the sum from n equals 1 to infinity of 1 over 2n plus 1 also diverges. Okay? So this one is kind of a little bit easier to use, right? It has different utility. Like, you can't just use this for every problem that's like this. Sometimes the comparison test really is your only way out. But often, when the comparison test can't help you much, this can. And vice versa. So let's do one more example of how this other theorem can be used. This one is going to be the sum from n equals 3 to infinity of n plus 2 over n plus 1 cubed. So we have n equals 3 to infinity, n plus 2 divided by n plus 1 cubed. Now, looking at my notes, it's clear that I took this example from one of the problems in the book, which means I didn't make it up myself. So you might be wondering, why does it start from n equals 3 rather than 1 or anything, actually? I don't have an answer to that. I didn't make this problem. But in any case, it doesn't really make much of a difference whether this starts at 3 or 1 or 2 or 15,000. Okay? Alright, so n plus 2 divided by n plus 1 cubed. Well, that's a little bit stupidly complicated, right? So, if you could decomplicate it, how would you do so? Well, for me, I look at this and I say, well, this would be a lot easier to work with if that 2 were gone and that 1 were gone. Both of them were gone. Okay? If that were the case, then we would end up with n divided by n cubed, which is the same as 1 over n squared. Okay? Now, the sum from n equals 3 to infinity of 1 over n squared, this is a convergent p-series. Okay, strictly speaking, we're leaving off the first 2 terms of the convergent p-series, but that doesn't make it not convergent, right? That's not going to change the way this works out. So we'll just say this is a convergent p-series. And now, okay, this is great and all, but I'm not sure how 1 over n squared would relate to n plus 2 over n plus 1 cubed. If you ask me for like an inequality that relates those two things, I don't know if I could give you one, at least not very quickly, not off the top of my head. But the limit comparison test allows us to just do this. What happens if we take the limit as n approaches infinity of, let's see here, let's say n plus 2 divided by n plus 1 cubed. All of this divided by 1 over n squared. Again, if this is positive and finite, then these two series have the same behavior. We know the behavior of this one, it's convergent. So if this is positive and finite, that's convergent as well. It might not be positive and finite, in which case we just have to do something else. So this is the limit as n approaches infinity of, well, I guess this would be n plus 2 times n squared divided by n plus 1 cubed. Now there are a few different ways to do this limit. I think the easiest way to do it is to just divide top and bottom by n cubed. If you do that, then this will turn into the limit as n approaches infinity. Let's see here. We're dividing the whole top by n cubed. So what we're going to get here is 1 plus 2 over n on top. And then on bottom, okay, we're going to get 1 plus 1 over n, and all of this is cubed. So now as n approaches infinity, 2 over n and 1 over n, of course, approach 0, which means that this becomes 1 over 1, which is 1. And that's positive infinite. So, by the limit comparison test, both series are convergent. In other words, the sum from n equals 3 to infinity of n plus 2 divided by n plus 1 cubed is convergent. And that is how we take care of it. Okay? So, that's all for today. Homework is up. Go ahead and get some practice on that.